And off we go. Okay, so here's where we were last time. We had just written down the definition of a double integral. Now let me remind you what the deal was there. I mean, why did we go to all this trouble? We went to all this trouble because we had, we thought we had it figured out. We had this idea of an iterated integral to compute, the volume under a graphed surface instead of the area under a graphed curve. Okay, sure. It seems like that would solve all of our problems, but in fact, we realized with this analysis here, this is a very narrowly useful construction. Iterated integrals will really so far only allow us to compute specifically volume under a graphed surface. End of story for the moment, right? You try to use it to compute something like mass, and it crashes and burns. You can't even start writing down on what's on the inside because the units don't fit. It just doesn't work, right? So we decided to then take this different point of view, which is to let's generalize the idea of a Riemann sum. Forget about this volume under a graph nonsense. That's usually not that important anyway. So the idea here was that we have some domain. The single variable idea that is you have a domain, and you're going to chop it up into pieces. Now, why do we chop it up into pieces? Oh, a lot of reasons. There's a lot of things that we want to compute on an interval where you can't really do it as a whole, but you can break it up into parts, answer the question on each part, and then just add them up. So the whole is the sum of the parts is what I like to call an accumulating quantity, right? And there's lots of accumulating quantities that we've computed with integrals by basically this, what I like to call the chop it up, add it up strategy, right? You chop it up into little pieces on which the questions are easy, and then you add it up to get the answer to the whole problem. Okay, so what we are doing with Riemann's with a double integral, that is just generalizing that sort of computational strategy, which is that if you have some accumulating quantity on a whole rectangle, now what's that going to be? Oh, I don't know. There's a lot of different possibilities, right? Maybe we're computing volume under a graph, I suppose, is one possibility, but maybe I want to compute the mass of this, or maybe I want to count how many bugs there are on my plot of land, or how many flowers would be a prettier question to consider. Millions of things, who knows, that might have this accumulation property where the whole is the sum of the parts, right? And if the whole is the sum of the parts, then I'm going to want to take this and chop it up into a bunch of pieces. Oh gosh, it's artistically harder than it looks. Chop it up into a bunch of pieces. Whole is the sum of the parts, and on each individual part, such as, for example, on this part right there, if I've got an easy answer, like, it's bugs per unit area times area. Or maybe it's flowers per unit area times area. What have you. Right? Millions of different applications. Easy questions to answer on each little piece. Whole is the sum of the parts. Right, so this is just ripping off the computational strategy of single variable Riemann sums, and the result is what you might want to call it, a multivariable Riemann sum. Sometimes I call it a two-index Riemann sum because we have I and J because we have two different directions in which to do that. Okay, so really this is all a double integral is. And in fact, I'm going to leave this all on the screen together. All a double integral is a whole is the sum of the parts strategy for solving problems, for adding up accumulating quantities. Okay, now with that intro done, today we are going to do our very first attendance check. Let's see here. So it is, I think it's past the, let's see here. Yeah, it's 11:05. Okay, so the quiz is gone anyway. So I'm just going to pass these out. All you got to do is just please write down your name on the sheet, and that's all it is. So let's see here. You could, works. Okay, here you go. You can pass those back. And then the right was here. So you came in after, so he doesn't need one, so pass him back there. Okay, so just write down your name and then pass them forward. That's all I need. Okay, back to the lecture. So, so we've got this new construction called a double integral. Let me get rid of that. Okay, there we go. And let's see an application of this. In fact, I'll just go ahead and zoom in. Now, it's tempting to say that we don't need double integrals for this because we already know how to answer this question. How do you compute the volume under a graph? Iterated integral. We already did it. Problem solved. We know how to get an answer, right? That's actually not my motivation here. I have an ulterior motive that I'll reveal in a moment. But let me just point out, whether you think we need to or not, I can compute this volume. Wrong tool. This volume under a graph, sitting over a certain rectangular domain by the typical chop it up and add it up strategy. So I'm going to take this domain. Now, very importantly, I'm chopping up the domain. I'm not chopping up the entire volume sort of in every direction. I'm just chopping up just the domain. And then I'm going to argue that the whole volume, the whole volume is the sum of the individual little volumes that I get over each little piece of the domain. So we take the whole domain, we chop it up into little pieces, sub-rectangles, right? And looking at the volumes over those individual sub-rectangles, the whole is the sum of the parts. Is that cool? Everybody see what we're doing here? See how that works? You chop up the domain, whole is the sum of the parts. Okay, let's take a quick pause on that. If y'all can go ahead and pass those big slips of paper forward, that's super. And I'll go ahead and set up what we're doing next here. So, great, thank you. Great to have all of them. Cool, all right. This is a sort of a brief summary of what we've done so far. Very first thing we did is we entertained the question of how do you compute the volume under a graph, and we basically, we came up with this. And let me just be a little bit more explicit. So we rewrote the volume as an iterated integral, and then we learned how to compute iterated integrals to get an answer. Okay, that was our very first thing. And then we said, shoot, that iterated integral thing looks pretty useful. Why don't I consider, I'll just take all these other applications and write them as iterated integrals too, except it doesn't work. This is the problem that we ran into where we're multiplying mass per unit area times length, and I don't know what that is, and is that an accumulating quantity, and how does that behave? What can I do with just lots of serious problems. So I'm going to say this just doesn't work. And I've already previously made fun of this idea that you can just claim that one physical quantity is, of course, equal to a totally different physical quantity with no justification. That's silly, right? That's just obvious nonsense. So you can't do that either. Okay, so then we said, let's look at this double integral construction, right? And the whole idea of a double integral, again, is you have all these applications, any accumulating quantity, whatever that might happen to be, and the whole is the sum of the parts. That's where double integrals come from. And that's where we were as of like 5 minutes ago. And then 4 minutes ago, we filled in a critical little step here, which again was just a silly example. My true ulterior motive. Why did I compute volume with a double integral? Why did I fill in this arrow here? When I already know how to compute volume, use iterated integrals. The reason I did that you look at this right here, if I know that volume can be computed by either double integral or iterated integral, that means that double integrals can be computed by iterated integrals. That sets up this critical step that I have in purple right here. And now we have a computational strategy that will allow me to compute tons and tons of applications. And that big picture strategy is, whatever your application is, write it as a double integral, rewrite that as an iterated integral, and then plug and chug. That's the final punchline strategy. And you notice that I don't make any nonsense arguments about claiming that mass is the same thing as volume, which of course is nonsense. I don't make any nonsense arguments about claiming that mass per unit area times length is somehow something that I can understand and make arguments with, because we don't. So we avoid all the nonsense. And now let me sort of get rid of everything that we don't really need to worry about anymore. This is our computational strategy that we've got. 3-step process. How we doing? Everybody's happy? Okay. Now, do let me point out, I know I say this a lot. I'm going to keep saying it a lot. You're going to get sick and tired of hearing it. But this is not a class about answers. Right? This is a class about ideas, about mathematical reasoning and mathematical understanding. Right? So this is not a how you get to your answer is kind of up to you sort of a situation. Right? It's just not. It's not what we do here. Kind of like history. In high school history class, in my high school history classes, it was if you knew all the names and all the dates, you're fine. Right? And that's not how history works in a real college history class. You have to understand concepts, and you have to be able to make an argument. You have to be able to make a case for how did this economic force in France in the 1600s cause the blah blah. I don't know any history, right? I'm making stuff up, but you have to be able to make such arguments. That's what history is about: understanding why things happen. I think, I don't want to overstate. I'm certainly not an authority on that. Well, math, anyway, again, it's not about answers. It's about the reasoning. So with that point in mind, let me show you a problem that happens. This is a problem that happens on a regular basis. Students have some question. They want to compute some quantity, whatever. That's the question on the test, let's say. And the very first thing said students write down, in some cases, is the resulting iterated integral, and then they compute, and then they get their answer and declare victory. All right, now what am I to make of this? Right, now you got to keep in mind this is a class about multivariable calculus. The tests in a class about multivariable calculus tests your understanding of multivariable calculus, and you cannot presume that the instructor will presume that you understand the multivariable calculus. This is where you demonstrate your understanding. Okay, so I know I'm being silly. So here's the problem. The student very likely might have actually been thinking this, but the student didn't write that. What the student actually wrote down is this, and that's not mathematically tight reasoning in this context, right? This is a bad look, right? To be perfectly blunt about it. So make sure you don't do that. I know it seems a little fussy because, but I know what the resulting iterated integral is going to be. Why do I have to write down the double integral that I don't need to keep track of in my mind to get an answer? And of course, the response to that is because the purpose of the question is not to get the answer. The purpose of the question is to give you an opportunity to explain your understanding of mathematical reasoning. And the reasoning goes like this. And you want to make sure that you distinguish yourself from students who think they can do that, right? And the only way, what I'm just saying, right? The only way you can distinguish yourself from this red argument is to actually write down the double integral. Now here's the good news. That's super easy. It's so easy. You'll see how in just a second, right? But this is a easy little requirement. All you gotta do is write it down. It's, again, show you in just a second. And if you do, then you're on the green path, and you've clearly distinguished yourself from the red path. Problem solved. Everybody wins. Everybody see my point there? All right, so let's do one. Let's see here. Okay, so we've got a 3-step process here. Now you'll notice this. Let me go back into the full screen. There we go. We've got a 3-step process. You can see 1, 2, 3, and step 1 is to come up with a double integral. Now here it is. There's the double integral. If you're computing mass distributed over an area. Now I've expanded this out in gory detail, just to show what's underneath what we're all going to eventually just kind of write down. You don't have to write down all of that gory detail every time. But just heads up, when we write this down, what you're actually saying is, first, that the whole is the sum of the parts. You're asserting that this is an accumulating quantity. You are then saying that mass is mass per unit area times area, which again, that's what mass per unit area does. It multiplies by area to give mass, right? So again, there's that. And then there is the recognition that, oh my gosh, look at this. This is straight up, literally, exactly the definition of a double integral. A double integral is a Riemann sum, which is what that is. Right, so that's what's underneath it all. In practice, it is perfectly fine to just go straight to that double integral. You don't have to show what's underneath it. Again, that was just for sort of instruction purposes. Okay, now before I go on to the second step, again, this is a lot more discussion than we'll usually give for these kinds of things. But I do want to point out a very handy notation. Very common. I use this all the time. It's extremely common. It's all over the place. And that is to recognize that, well, look, eventually we're going to have a double integral. In a double integral, the limit of the summation is going to be sort of represented by this notation. So, all right, well, how about when I make my very first step here and claim that the whole is the sum of the parts, how about here already I go ahead and replace that summation with a double integral symbol. And so it's just a shorthand. It is arguably a little sloppy, but everybody knows what you mean when you write that. Everybody does it. It's very common. Totally fine, and I encourage it. So instead of writing down stuff like this, I prefer to write down stuff like this. It's just a little bit easier to write down, a little friendlier looking. Right? So I'll show you another example of how useful this can be in a minute. Okay, so we have talked now about what I'm going to call step 1 of the argument. Let me remind you, that's up here. That's step 1. We've turned an application into a Riemann sum. Step 2, apparently I'm going to have to turn the double integral Riemann sum into an iterated integral, and we have a theorem for that right here. This is just the explicit acknowledgement of what we already said. You have a double integral. It's equal to the corresponding iterated integral, and the bounds are exactly what you would expect, and it's exactly what you would hope. The integrand, you'll notice, for the double integral, is exactly the same as the integrand for the iterated integral. It's exactly what you would hope. So step 2 is, in this case, quite easy. There you go. Right, let's see where I'll put the 2 right there. Step 2, double integral is iterated integral. Oh, yeah, question.
So given that this is a rectangular shape,
Yep.
you could write that like flipping the pounds.
Could write what?
You could write step 2 by flipping the pounds.
You could. Oh, yeah. If you want to do this, yeah, you have your choice. Absolutely. So indicated here. I mean, take either one of these iterated integrals to yourself. Yep. Okay. Now let's see here. Step 3. We need to compute the iterated integral of the fundamental theorem, and you know what? We already know how to do that. That's just. I'm not going to repeat a bunch of. Wrote a bunch of, mechanics, right? Y'all know how to compute double integrals, and it's just, don't forget what's a variable and what's a constant. Don't forget to plug the right values in for the actual variable, and don't forget how to do single variable calculus. It's all familiar stuff. Okay, so in practice, again, I wrote down on this example way more than you will in practice. In practice, what I want to see is mass is double integral, is iterated integral, and then, there's going to be details where you plug and chug to get the answer. All right. Okay, so let's talk about this shorthand. I'll be real quick with the shorthand discussion here, but this idea of using integral notation as you develop a Riemann sum. Here's an example of how useful it can be. Here, there's a bunch of details in this example, but the big idea is I want to build a wall. I came up with this when literally we were building our house that we currently live in, and there's kind of a stone facade there in the front, and at some point I looked at they had all these little stones, and they were sitting all over the yard, and I just thought to myself, oh my gosh, somebody's going to have to pick up those stones and lift them up to, man, that's a lot of stone. Oh my gosh, that's a lot of stone. That's going to take a lot of work to pick up all those stones. Just the lifting, not even the construction part. And so it occurred to me, hey, I'm just for fun. I like to compute stuff, and I see little opportunities like that. And how much work does it take? How sorry should I feel for those guys to pick up all those basically big bricks? So that's what this question's about, and here's the part I want to talk about. Now again, there's a lot of details, and you should read through the details and follow through the details. But the big idea is that the grand total amount of work, yeah, that's a whole with the sum of the parts kind of a deal. The total amount of work it takes to lift all the stones where they go is the sum of the individual amounts of work that it takes one brick at a time. Physical appeal, right? I think that's pretty believable. Whole with the sum of the parts. So dW here represents the total amount of work that it takes to lift that brick from here to there. How much work does that take? Well, work is force times distance, and you will notice that the distance is, well, whatever the height of that brick is, which is its y coordinate. So that just says work is force times distance. Now I got to figure out, okay, what's the force? How much does that stone weigh? Oh, okay, well, the weight, and keep in mind, weight is usually around here anyway, measured in pounds. And tragically, confusingly, we also use pounds to represent masses, which is not really very natural. And so there's this do you multiply by g thing. And if you've had a physics class and you're worried about the do I multiply by g, in this case we don't have to, because weight is already force, and the whole purpose of multiplying by g is to convert a mass into a force. It's just not our problem here. So how many pounds is that brick? Well, pounds is pounds per unit area times area. However much area of the wall that brick covers, pounds is pounds per unit area times area. And what is the pounds per unit area? Well, that was, I've already used that color. Sorry, hang on. That was given. So that's where that comes from. Okay, now, details to follow, details proceeding, you got to set up your axes, blah, blah, blah. But notice, as I developed the Riemann sum, as I took this sort of broad statement of, work is an accumulating quantity, the whole is the sum of the parts, and as I developed that one step at a time down to an actual double interval, that shorthand notation was nice and handy. Just notation, yeah.
In a normal exam question, will we have to assume that equation is for weight or?
No, I'll specify, and if I fail to specify, I am highly fallible. Right? If I forget, right, just come up and ask, and I'll be happy to elaborate. Yeah, and of course, now it may be indicated, but in a subtle way. Like if it says density is blah 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 formula in units of pounds per square inch, right? Then that's the giveaway that it's a force and not a mass, right? But if it's just a formula and there's no units given, and if I don't specify anywhere else, then you just want to ask. Yep.
What's the significance of the second part of the question? How much work does it take to build the ones materials?
Yeah. Right. So that pertains to the question of how far do I have to lift it? Because if the stones start at this height, but then each stone has to get brought up to that height, knowing that it starts there is how I can conclude that the height I had to raise it is y. Otherwise, if they were sitting on a table, right, that had height 2, right, then they wouldn't be here, they'd be here, and that distance would be y minus 2. Is that cool? Yeah.
We're trying to build a wall, but we're lifting stones inside the wall. Like that stone would be inside the wall.
Yeah. Well, it's true. So I'm gonna have to lift up the stone, and then yes, I am also gonna have to horizontally move it into the wall, and that's not. In real life, that's work because it's heavy and I got to hold it. But in a physics sense, that's not work. And me sitting there and straining to hold it as I move it horizontally is just me being inefficient. What I should have done is I should have picked it up and put it onto a rolling cart and then just effortlessly roll it into that.
No, in terms of the edges are the wall that we're trying to build, right? We're not.
No. This is the wall. Y is up. This is not. We're not looking down at a horizontal thing. No, this is the up direction, and this is right. Left, right, up, down. So this is the wall.
So the wall is like above us.
The wall is like this chalkboard.
Oh.
Yeah.
And that's the depth of the wall.
Yeah, that's what this is. Yeah, that's right. So I'm picking up stones and I'm putting them to make the wall. Okay. All right. So this notation, very handy. Heads up, you're good. But sometimes students get confused, especially when you write down something like this and they're like, DF, where's the F axis? Kind of looks like there should be an F axis somewhere. And it isn't, there isn't an F axis, not relevant to this picture anyway, and that's just not what that DF means. DF in this case just means a little bitty piece of weight, aka force. Okay, moving along. Here's where things get fun. What if your domain's not a rectangle? Right now, if we do have a rectangle, we pretty much have that problem crushed. This is how, if you've got a rectangular domain, write it as a Riemann sum, aka double integral, rewrite it as an iterated integral, and then plug and chug. So this is the roadmap, right? Oh, what are we going to do with a non-rectangular domain? And we kind of have to start all over. That's the bad news. Got to start all over. Here's the good news. Everything's the same except for one little micro detail. Here's the argument. I got a weird shaped loaf of bread here, but it remains that I can cut it into slices. Right? Most loaves of bread do not have a rectangular footprint. So the whole is the sum of the parts. The parts are all slices. The slices are all cross-sectional area times a width, just like when you have a rectangular domain. And those cross-sectional areas are still the area under a curve, right? I'm still looking for the area under a curve. The area under a curve is still computed by an integral. Oh my gosh, everything's pretty much the same. There is one little thing that's importantly different. The one little thing that is importantly different is the inside bounds. So, in particular, if I want to know, for example, let's look at the upper bound. I think it'll be easier to see that upper bound. And how does that upper bound depend on y? Right? Well, for this value of y, we get that upper bound, as you can see from, because that's where your integral is going to end. You're going to end when you get to that purple point, and whatever its y-coordinate is, that's the upper bound for that integral. But, check it out, if I looked at a different value of y, let's say there. Okay, well, I'm not going to be computing over all of these values. I'm going to be basic. Let's see if I can draw this. It's going to be something kind of like, that's the worst straight line ever, but there's going to be, let me do better than that. Good enough. That's going to be that's going to be the last point as I sort of go through that slice, and that point will have a different, not that value of y, it'll have a different value of x, different value of x than we had before, because we're coming from a different point, because we're looking at a different slice. So that's the big revelation, the big difference. The only thing that really matters when you have a non-rectangular domain, the inner bounds, in this case the x bounds, as I do the inside integral, the x bounds in general, the inner bounds are functions of the outside variable. That's it. Everything else is pretty much the same. Now there's formalities to worry about. How do we define a double integral, and how do you, there's an annoyance of notation and stuff like that. That's formalities that we don't need to worry about. A double integral is still morally exactly what you think it is. You take your domain, you chop it up into pieces. Don't bother me with the little details of how we chop it up just chop it up into pieces, right? And then add up over those pieces. A double integral remains just chop it up, add it up, right? But in terms of in practice, what's going to be different is, as what we said here, that the inner bounds are going to be functions of the outside variable. Did I see a hand somewhere? Yeah.
I just wanted to clarify.
Yeah.
Well, even in this case, it would still be valid to switch it, just the functions would change.
Yeah. That's right. So you can always slice in either order. It's just, as you say, the bounding functions would be different, and other considerations can be awkward. Yeah, here's what would get weird if we slice this in the other order. Let's suppose that I switched these.
Because
you get some. Yeah, that's right. So you would get, for, let's say, for a certain value of x, let's say this value of x, you would actually kind of get two separate slices, and you're going to have to deal with that, and it can be annoying sometimes. But so you can go ahead. I don't advise it, but but I should say you may, but you don't want to. Yeah. Okay, and that's going to be one of the big things we're going to talk about, by the way, is how do you make good decisions as to which way to slice. In this case, I think it leaps off the page which way you want to go. I mean, but in different cases, there are different incentives. Yeah.
Can you explain again why it's a function of y?
Yeah, well, sure, because, I mean, roughly speaking, the point is this upper bound, what that value of x is going to be, keep in mind it's a value of x because it's a bound on an x integral. It depends basically on where that point is. And that point has different x coordinates depending on where that point ends up being as we move along that curve. Right? So it's literally because that edge is not a straight line. It's literally because it's not a rectangle that we get that the bound's a function of the outside variable. Yeah.
What if our domain was an ellipse and we don't have a specific interval there? We just use the same matrices and minus them.
Oh yeah, but you do. Yeah, we'll actually do one that'll be kind of like that. Yeah. So let me say the answer to that will come out in some examples. Yeah. Totally. It's going to be totally fine. Okay. Now there's a big takeaway from this analysis that we gave. You'll notice that as we spent time worrying about, okay, here's our problem, right? We've got to figure out what these bounds are, and here's the bounds, and it comes from certain points on certain curves that we can identify, certain values of y between there and there. Notice the entire conversation happens in the xy plane. And what's going on in this direction? Right? How high this is? I mean, whatever. That's the integrand. We already know what the integrand's going to be. The integrand is whatever it's whatever it is for the application we're interested in. The integrand doesn't change because the domain is weird. So we don't need to worry about it, which means we don't need to draw it. Which means we did not need to do all of this analysis on a three-dimensional picture. That was arguably comforting because, again, we like to think in terms of, we got this, I like to be able to see all the players and here's our loaf of bread and all that stuff. But all that's going to change is these bounds, and those bounds entirely are determined by a two-dimensional picture. So that's going to be the next take I'm going to give you. Notice I've kind of redrawn all of this here, and this domain, right? Well, I don't have to see it as it sits inside of the xy plane in space. I can just say, well, there it is in the xy plane. All I'm going to do to it, right, is look at different values. Let's see here, different values of y. And for each of those different values of y, I'm going to identify the corresponding points that give me, yeah, that's right, the x coordinates, oh gosh, what color to use? I'll use orange. These x coordinates that are going to be my inside bounds. So no need to draw this much more difficult picture. I can just literally see it like this. Just look at the domain in the xy plane itself. You don't need to draw the graph. The graph, in fact, not only do you not need to draw the graph, drawing the graph is a problem. It turns what really should be a two-dimensional analysis into a much harder to draw three-dimensional picture that I then have to analyze. And why would I do that to myself? I'm just shooting myself in the foot at that point. Right? Just draw the two-dimensional picture. It's got everything you need. And it looks a little different, right? And it doesn't have that element of being comforting that I can straight up just see my loaf of bread and my slices of bread, etc. But we can still say just as well, for any given value of y, here's the associated points, and from that, and we'll talk about details we'll solve for our corresponding x coordinates, which are our bounds. Okay, now how that process works, I like to summarize as follows. This lower bound, well, it comes from understanding that point. Wait a second, where'd that point come from? Well, that point came, given a y value, that point came about because that's the point, that's the start of my slice for that value of y, and it is the start of the slice because it is on that curve, which of course has some equation. And if you want to know what the bound is, right, how am I going to find that bound? Well, you just solve for whatever variable that is, and in this case, I get this to cooperate. There we go. In this case, that is an x coordinate. It is a lower bound for x. So you solve for x in that blue equation. Solve for x as a function of y, and that gives you the corresponding bound. So this is the nice little pithy little summary. I like pithy little summaries. Whatever bound you want, identify the corresponding point, identify what curve it's on, write down the equation, and then solve that equation. That's the process. Okay, let's do one. Okay, let's see here. I can zoom out a bit. Not that much. There we go. Okay, so we've got a domain now. Our domain is a certain triangle. And before I go into any details, let me sort of rewind a little bit and talk about the context. Wait a minute. What are we computing here? What, are we computing? It didn't say. Are we computing a mass? Are we computing a population? What's the stuff in question? So just to resolve that concern, let me just note, all we're going to do in this question is just step 2. All right, I'm going to presume that the question comes with a double integral already made. So why am I interested in that double integral? Okay, that's a backstory. Whatever, it's not really relevant to the problem. Right? The question is about computing a double integral. That double integral could be useful for computing many different things. Who knows? Not part of the problem. And so what we're going to consider is just how to turn this non-rectangular double integral into an iterated integral. And then, by the way, we're not going to do the plug and chug at the end either. That's, again, could if you really wanted to know the actual answer, but our focus is going to be on this step in the process here. Okay, so here we go. So I'm going to do this both ways, by the way. Arbitrarily, I'm going to start by doing my x slicing first. I almost said first. I'm going to do my x slicing on the outside first in the slicing process, which means I'm slicing like so in that direction, for which our slices look like that, for which then our first slice is here, where x is obviously 0, and our last slice is there, where x is obviously 1. Just read it straight off the givens. Okay, now here's where we apply the method from above. Now assume we have some fixed value of x. And now we're going to try to figure out what our y bounds are. Right? What goes... Oh, and let me conceal the answers here for dramatic purposes. How am I going to figure out our x bounds? What goes there and what goes there. Okay, well, let's start with the upper bound. No particular reason. That upper bound comes from this point. Right, as I'm doing that particular x slice, that is my last point on that x slice. That point is on that curve, that curve has that equation. Solve. Now be careful. Here's where it's easy to mess up. Super easy. I see this mistake made a lot. Big landmine here. Don't forget what you're solving for. We are looking for a y bound. We're looking therefore for a value of y. This is the upper bound for the y integral. So in this equation, we have to solve for y as a function of x. And, sometimes, because they lose track of things, students solve for x as a function of y and put the wrong thing, put y in here. We're not interested in how x is a function of y on that curve. We're interested in how y is a function of x because we're looking for a y bound. Is that cool? Everybody with me? Okay. So, yeah. So, y is a function of x, like so. That is our y bound.
Where are we getting y equals x from?
Oh yeah, from just from the given. So I have the coordinates of these vertices are given, right? And so I know that point and I know that point, and y'all know algebra 1, and so find the equation of this line, and that's what it is. Yeah. Is that satisfying? Yep.
What is the quantity? What is the integral represent?
Yeah, I don't know. That was what I was saying earlier. We were given an integral with an integrand, and where did this come from, and why do we care? That's some application. I don't know. That would be what is the application that gives rise to that integral? It didn't say, but I also don't need to know, because the question just is, what we're interested in here is how to turn a double integral into an iterated integral. Yeah. Is that cool?
Yeah.
Yeah. Okay. Alrighty. Okay, lower bound, I'm going to do much more quickly. My goal with that first one was just to talk about, I wanted to make sure to underscore the process, right? By the way, please, I urge you, strictly adhere to the process, because it's so easy to kind of whoopsie, or to, I solved for x instead of, I shouldn't have solved for x as a function of y, I should have solved for y as a function of x. And you'll write down nonsense that doesn't make any sense. So again, like for example, if you were to, in this equation here, if you were to solve for x as a function of y for some reason, and if you were to then say, I'm going to make this bound here, then y, that doesn't make any sense at all. We would have a y integral then, y being a dummy variable that goes from 0 to y. I don't know what that means. Y isn't determined. X is the thing that's determined. Right? So if you put a y there instead of an x, simply by solving for the wrong thing here, you get nonsensical garbage. So it's a delicate process. It's easy to mess it up and accidentally write down nonsense. So be sort of diligently, meticulously follow the process and keep track of what you're doing at every stage. Okay, all of that said, let's do the next one. How do we find the lower bound? Well, this lower bound comes from that point, because that's the first point as we do our x slice. That point's on that curve. That curve has that equation. Again, sort of easy algebra, right? What am I doing here? Why am I here? Well, I'm solving for a y bound. We're looking for the lower bound in a y integral. So I solve for y. Again, easy to do, right? In this case, the algebra is trivial. And whatever I get in solving for y, that is my lower bound. Okay, now let's do it the other way. Let's slice it up the other way. Instead of dy dx, let's do dx dy. All right, well, one step at a time, starting with y. Y y slices look like this as we move in the y direction, as we look at individual values of y. Those are what the slices look like. And again, sometimes the details are just right here looking at us. This is obviously where y is 0, and this is obviously where y is 1. Sometimes the fish just jump in the boat. Right? The outer bounds very often are pretty straightforward. Now, as usual, we're going to fix a value of y. And now we're going to ask, what are the bounds for x? What's my starting value of x? What's my ending value of x as x moves across that y slice? Okay, well, let's see. Yeah, let's do this one at a time. X1 comes from that point, which is on that curve, which has that equation in which, gosh, it's so easy to lose track. It's so easy to lose track. I'm looking for an x bound, so I have to solve for x as a function of y. And how is x a function of y? Well, like so. Is that cool? Lots of students will put x there. And again, wrong and nonsensical. Okay, now looking at the upper bound. Again, for some value of y. Want to find the the upper bound for x. Well, the upper bound comes from that point, which is on that curve, which has that equation. Wait a minute, what am I doing? Oh yeah, that's right, I'm solving for x. So I solve for x, easy to do, and whatever I get is my upper bound. Yeah?
Let's say we didn't have x plus y and we get the rest like the same way. Would that give us the area of a triangle?
The what now? Oh, you're saying if this were just 1.
Yeah.
Yeah, then that's right. And in fact, here's the best way to see this. My favorite way to see this is that this would then say that we're literally adding up a bunch of little areas. And so, yeah, you get the whole area because you're adding up all the little pieces of area. Absolutely. Yeah. Right. Okay, now I've got a bunch of examples to follow. Again, we're going to go through these increasingly quickly, increasingly fast. Because it's kind of all the same thing. And really my incentive here is not to rehearse the exact same process every example, but to point out specific details, specific landmines. And I want to show you all how to circumvent said specific landmines. Right? So let's do this one. Again, we're going to slice both ways. We're going to do it quickly, and then I'm going to talk about why this is a cool example of what you can infer, what strategy, what clever, inference you can draw from the example. So here we go. Again, we're converting a double integral into an iterated integral. So again, this is sort of just step 2. We've got this curve, and we've got this curve. Oh, I do have to talk about the terminology here. Our domain is the region that's bounded by. Bounded by means 2 things. It means that the curves in question make up the boundary. It also means that the region is bounded, that you can put a fence around it. That it doesn't run off to infinity in any direction, right? So don't make the mistake of picking this region up here, for example. This region here is not bounded by the green and blue curves. The green and blue curves make up the boundary, but this yellow region is not bounded. I cannot put a fence around it. It runs off to infinity in some direction. It's not what we're talking about. So there is, in fact, only one region that is bounded by these curves, and it's that region right there. Now, just another heads up. That's part of the question. All right, so that's going to be on you. That's part of your job when you see a question like this, is to interpret correctly from the statement of the question what the domain is that we're talking about. So sadly, I do see it happen sometimes that students blow a little too quickly through the statement of the question and start getting into the mechanics of and then it turns out, they were looking at the wrong region. And it's heartbreaking to see that, right? So make sure that's not you. Do go ahead and invest the extra 10 seconds in making very sure that you've read exactly what the question says and that you've interpreted correctly what the region in question is. Okay, all right. So let's do it dy dx just to get the ball rolling. X has slices that look like this. And now I do have to do a little bit of work this time to figure out what those bounds are. This upper bound, well, that upper bound comes from where these two curves intersect, which means that to find this upper value of x, I'm going to have to solve for x. Here, let me do it like this. I'm going to have to solve, to get that, I'm going to have to solve for x in that pair of equations. And now, of course, if y is that, and y, x squared equals 4, blah, 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 solve for x, and you're going to get x equals 2 per the picture here. Right, now what about the lower bound? Well, the lower bound comes from this point, which again is a point that's in the intersection of the exact same two curves. Again, I need to solve for x because we're looking for an x bound. The tricky part here is a lot of students, again, misunderstand what square root means, right? Square root, there's the square root function, and then there's the idea of a square root. And there are two of them. The answer that we're looking for is clearly one of the square roots of 4, which means it's either 2 or negative 2. And how do I decide which one it is? Well, the picture pretty clearly shows me that the lower bound I'm looking for is clearly negative. And so I choose the negative of the 2 square roots. Thank you, picture. Is that cool? All right. Okay, all right, so that little bit's like so. Let's see here. Now we're going to fix a value of x. We're going to look at that x slice. For that value of x, I now want to know what's my y1 and my y2. And, well, those two bounds come from these 2 points, which are on these 2 curves, which have these 2 equations. Wait, what am I doing here? Oh, that's right. I'm solving for y because I want y bounds, and thankfully, the y's have already been solved for. And so these y's here are your bounds. And the tricky bit here is make sure you get them in the right order. The way I drew this figure, I'm pretty sure I did this on purpose. The figure kind of makes it look like 4 is the lower bound and x squared is the upper bound, because I drew the equations after the curves had crossed from the part that we actually care about. Right? So see right here, x squared is the lower bound, 4 is the upper bound. Easy whoopsie. Right? Does that make sense? Everybody happy? Okay, let's see, doing the other one. Okay, no big deal. Y, pretty clearly, goes from 0 to 4. Then we fix a value of y. Our y slice goes like this. I need to know the corresponding values of x. Those x bounds come from these points, which, oh, hey, check this out. They're both only on that one curve. In that, I'm going to need to solve for x. Solving for x, a common screw-up. Very common mistake is students will say, oh, yeah, it's y equals x squared, and so they put x squared for these inside bounds, because it's on the curve. And a lot of students find this curve is x squared. Right? Not how the process works. You gotta play the game. You gotta do the process. We are looking for x bounds. We have to solve for x as a function of y. And again, obviously one's negative, obviously one's positive. So you get these minus and plus square root of y. Everybody good? Okay, so again, that was quick. What's the purpose of this example? Well, it's a little more practice, I suppose. The main purpose of this example, though, is to let's try to look back on this and speculate, hey, which was the better approach? Which of these two iterated integrals do I like better? And how can I hopefully do it the better way instead of the worst way without having to do it both ways? Now, I have a strong preference on this. I don't like this one. Because check it out. When it comes time to doing the y integral, my integrand is going to be whatever this x integral works out to be, and I can tell you, I can see it coming, right? When I do the x integral, I'm going to do an x antiderivative, and there's going to be a bunch of x's in here into which I'm going to plug in some square roots. I think this dark green integrand is going to be chock full of square roots. And do y'all remember in Calc 1, Calc 2, whatever, when you're learning, single variable integration methods, when there's a square root in your integrand, that stinks. It's not that it can't be done, and sometimes it's fine. All else being equal, most of the time, day in and day out, try to avoid getting square roots in your integrand. Right? And if you don't want square roots in your integrand of your outside integral, you don't want square roots in the bounds of your inside integrals. So let's try to trace this back. What was the original mistake? How did I get these square roots in this? Well, I got these square roots because I had to solve for x as a function of y in this equation. That's ultimately where it came from. I chose to put the differentials in an order where I would have to solve for x. Putting the dx on the inside means you're going to have to solve for x. I don't want to have to solve for x. You look at y equals x squared. Would I rather solve for y or would I rather solve for x? I'd rather solve for y. Much better. Right? So this is the takeaway, and that is, look at the equations that you're given. Look at the scariest equation that you're given, you might say, and ask yourself which one of those variables would you rather solve for. Whichever one you'd rather solve for. In this case, I would much rather solve for y. Okay, we'll put that on the inside, because whatever you put on the inside, that's the one you're going to have to solve for. Does that make sense? Now, this is not a law. This is not always. This is a good rule of thumb. This is a good sort of you're going to come up with more wins than losses if you follow this rule. Okay, here's another one. Again, we're going to do it two ways. Again, we're going to learn a lesson. You could put the dy on the outside, representative of doing your y slicing first, for which y slices look like that, and blah, blah, blah details, and you end up with this. Okay, whatever. Or, what if I put the x on the outside? Now, it's tempting to say, well, x goes from 0 to 2, and it kind of does. Here's the problem. For the first so many values of x, as x goes from 0 to 1, my y upper bound is going to come from that curve, which will give me this formula for my y upper bound. But for these values of x, as x goes from 1 to 2, my upper bound for y is going to come from that curve, which has a different equation, and you're going to get a different formula for that y upper bound. Everybody see how that happened? The details, of course, right? But the curve from which I get my y upper bounds is a different curve for different values of x. And so when that happens, what do we got here? Well, now we've got two different. I could compute this one interval here, or I could compute two separate intervals here. And again, all exceptions granted, and weird stuff happens, and sometimes the algebra might be easier in one or the other, who knows. But most of the time, again, if you had your choice, would you rather do one interval or two intervals? Most of the time, you want to bet on one interval, right? So, so again, how do I anticipate this in advance? I don't want to have to do it both ways and then subsequently make my choice. How do I see it coming? And here's my take on it. As you're going in the x direction, as I'm looking at x slices, I sliced through a corner. Here we go. And if you think about it, where'd that corner come from? That corner happened because two curves intersect. And it is the fact that these two curves are intersecting that allows my upper bound point to sort of jump from one to the other. So I think this is a pretty efficient little rule. Whichever variable you put on the outside, however you do your slicing, try to make sure that those slices don't slice right through a corner right in the middle of your slicing process. Now, of course, you're going to start at a corner, you're going to end at a corner. That's cool. At the start, you were starting a new interval there anyway. That's not a problem. At the end, well, you were already done, so who cares, right? But in the middle of your process, try not to slice through a corner. And notice in the one that worked out well, we didn't, right? Where we had y on the outside, y was going from 0 to 1. None of our interior slices touch corners. Just the start and end. Yeah? Cool. Okay, here's a weird one. Sometimes the domain isn't even given. Sometimes you got to figure out the domain for yourself. So here you go. The question says, let's compute the volume that's in between two surfaces, and so in particular in between that paraboloid and this plane. And you got to use your imagination. Think about the geometry. And by the way, that's unavoidable. This class is unavoidably, intrinsically geometric. Visualizing in 3 dimensions is what we're doing in this class in some sense. So there's no way around the geometry on this. You got to be able to think geometrically. You got to be able to draw decent pictures, because a decent drawing will help you visualize the geometry. Okay. All right. So, okay, well, the first part of this problem is not so bad. I'm going to argue first that these little volumes here, if I add up those volumes over a domain, that's what I'm going to call the shadow underneath the volume in question, right? You chop up this shadow into a bunch of little pieces. Over each piece is a certain amount of volume, and the whole total volume is the sum of those individual volumes. The grand total volume of French fries, right, is the sum of the volumes of the individual French fries. Okay, so that part's no big deal. Then let's see here. Let's talk about what is the volume of that French fry. Well, this also not so bad. If you think about it, this volume here is going to be the height, which is just the difference of these two z coordinates, That gives me the height. And then I'm going to multiply that by, well, the area of the little projection. That, the area of the base is dA. It's a boom, double integral. That part's pretty straightforward. Here's where it gets fun and a little different, and that is, what is this domain anyway? More to the point, what is this curve that is the boundary of my domain? It's not given. So here's how I encourage breaking this down. Again, you got to have a decent picture. A decent picture is invaluable. In this case, because of the picture, I can see that this curve is literally the shadow of this edge. You might call it an edge of our shape. That edge is the collection of points where that equation is true and that equation is true. Right? It's where the blue surface meets the green surface. Is everybody buying that? Now let me show you the landmine. Lots of students step on this one. I'm sympathetic. I understand, but it doesn't make any sense at all in retrospect. And so again, be honest with yourself as to whether you might, be prone to stepping on this following landmine. A lot of students will solve a pair of equations by setting the two equations equal to each other. It's absolute nonsense. Okay, but a lot of students will say, okay, I want that to equal to that. Actually, that has nothing to do with anything. Why on earth would you do that? It makes no sense. Just for fun, let me point out how silly this is. If I want to know, if I've got two equations. If I want to know in which cases are these equations both true, would it be fair to say, well, I want to know where 3 is equal to 7? No. Nonsense. It's not a thing. It's got nothing to do with anything, right? So don't make that mistake. What you want to do here is realize that you're looking for points. You're looking for points where the height up to the paraboloid and the height up to the plane are equal, and that means that here's the height up to the paraboloid, and here is the height up to the plane. When you want to find the points where those two heights are equal, you want to set that z equal to that z. So literally what I would suggest is different ways you could do it, but you could solve for this z and plug it into there, or you could take this expression for z and plug it into there. Either way, and what you get as a result then is some algebra that you can solve, and that'll give you the equation that you're looking for. Everybody see the process there? Just make sure not to step on that land. Don't set equations equal to each other. It's not a thing. Right? It doesn't make any sense. By the way, quick reference, you'll notice that this does involve completing the square. Do y'all remember completing the square? For whatever it's worth, a lot of students come into this class and don't know how to complete the square. And I suspect that somebody made a decision that was not important, and somebody removed that from high school algebra classes or de-emphasized it. They make decisions for their own reasons. I think that's a terrible decision. I think completing the square is very important. It comes up here and there. I mean, this is a pretty reasonable scenario, and notice you have to complete the square to be able to put this into a form where you can recognize. By the way, this is easy to recognize. It's just the equation of a circle. Yeah.
So that equation is like the domain where
Yeah. So this equation is the equation of the boundary of our domain. Yeah, and so if you want to finish turning this into an iterated integral, you have to decide which way you want to slice, look for the corresponding starting and ending values, and then look at slices and solve for one variable in terms of the other. It's the usual process. Yeah. Right. Yeah.
Should the French fry that we've drawn extend down to the XY plane?
No, because what we're interested in computing. Let me get this to cooperate. Whoa, here we go. We're interested in computing this volume here, right? I am not interested in computing this volume, right? Does that make sense? So I got to figure out, how is it that I'm going to distinguish? I don't. All this stuff down here. This is not sort of part of what we're interested in. And so the way we do that is, this is our French fry. It starts where the plane is, and it stops when we get down to the bottom. The bottom of the French fry is on that paraboloid. And there is no French fry underneath, right? Underneath, there is nothing down there.
Oh, it's just like in the picture, it looks like it just stops in the middle.
And there's this problem that when you use a two-dimensional, flat two-dimensional screen, to try to draw a three-dimensional picture, it's hard. Yeah. So the intention is that this green point is on the paraboloid, and this blue point is on this plane.
Got it.
Yeah.
And also, so we got an equation of a circle, but the intersection is like a rotated circle, right?
Whoa.
So
the intersection what?
it's like a rotated circle.
I don't know what you mean. I'm sorry.
Like
So
the
this.
intersection of the plane and the paraboloid is like a circle rotated along the.
Oh, yeah. So this is the actual intersection, right? And what I did here by eliminating the z's, right? By plugging in one z's formula into the other z location, that's called eliminating z. And so what I get is still a true relationship. I mean, this purple relationship is valid for every one of these points, but it's only talking about the relationship of the x's and the y's. And so this doesn't tell me anything about the z's, and conveniently, that's exactly what I want. I want to know just the relationship between the x's and the y's.
So it's like a projection of that circle
Yep.
onto the x y.
Yep, that's right. Okay, we're out of time, sorry. So we'll call it a day here. We're finished now with section 5. Oh gosh, I lost track. Is that right? Okay. So we did today 5.1 and 5.2. 5.3 is a quickie, and we'll get into 5.4 tomorrow. See y'all later. Have a good one.